Okay, this is part two of rates of reaction. Okay, so oh gosh, why is everything going wrong now? All right, so we're good there. Are we all good? We're all good. You said you were good a minute ago. I'm assuming you're all good now. So let's have a look at the next part of the question. Okay, now, all right. Well, we can do things with this, even though the question, believe it or not, doesn't ask us to. All right, now let's go to hundreds. Make this smaller, like that. All right, we're good. Now, let me move that down a bit. Now, interestingly, we can, using the thing that we've just got above, we can use that to give us what's called the rate equation, the full rate equation. So, the rate equation, what is the rate equation for the above thing for this? All right, it's R, that's the rate, equals some constant times the oxygen times the nitrogen monoxide. That's it. Okay. Now, well, it's not it, is it? Now we have to put an exponent there. So are we good? So that's the rate equation. It is a third order reaction. All right. Are we good? Are we good there, guys? Are we good? 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 Oh gosh, I can't see. I'm asking you if we're good, and I can't see. Are we good? Sorry, I wasn't looking at the right screen. All right, I've got two screens. Actually, I might get a third screen if I can fit it in somewhere. I love having screens. I like pretending I'm on a spaceship. All right. So, deduce giving a reason whether the following reaction mechanism is possible. All right. Is that possible? Is that possible? Is that a possible reaction mechanism? What do you think? It's a yes or a no, guys. What do you reckon? And don't be scared. If you don't know, just say IDK. We're not here to judge anyone. Do you know what the rate equation means? Thanks, Lungi. And Helena, you've got to say I don't know as well. All right, we've got to move things on. Do you know what the rate equation means? And this is a beautiful thing in chemistry. Okay, let's do an analogy. Okay, all right, let's go to South Africa. Okay, all right. Now, is that a good one? No, that's not a good analogy because it takes quite a while to get there, doesn't it? Let's go shopping. All right. And what do we want? We want to go to Spa and we want to pick up some baked beans. Okay. And it's a busy day. Are you with me? So we're going to go to Spa and we're going to pick up some baked beans. All right. We know where the baked beans are. Okay. So there's two things we've got to do. We've got to go into the shop. Well, that's not, let's ignore that thing. But once we're in the shop, we've got to pick up the beans and we know where they are. And then we've got to pay for them. Okay. Now you know exactly where the beans are, but it's a busy day. Yes. So, what of those two? What's the other thing we must do after we've picked up the beans? What have we got to do with the beans? Exactly. Yeah, queue and pay. Exactly. You're both right. Now it's a busy day. So picking up the beans is, I don't know, 2 seconds work. Paying is 10 minutes. Do you understand? If someone is outside, yes, and asks, where the hell have you been? Are you going to say, oh, it was a long queue? Or, oh, it took a while to find the beans? Don't forget, you knew where the beans were. Yeah, you're obviously going to say the queue. And the point I'm trying to get is probably not very well. The thing that determines the rate or the thing that determines your time in the shop wasn't picking up the beans, it was the paying. It was the slow step that determined your overall step. Does that make sense? Even though it's a horrible analogy. Yeah, thanks, Elodie. I think you're being kind again. All right. So the rate equation, because this is the rate equation, let me think, this thing here, oh, that's not good at all. The rate equation, this must include the slow things. Somehow, these things are in the slow step. Why are they in the slow step? Because they tell you what the rate is. The fast things don't tell you what the rate is. The slow things tell you what the rate is. Now, we have a special term for these slow things in chemistry. If I can get a nice bright color here, it's a scary color. We call these the rate determining steps. Okay, and then often called the RDS. Now, very, 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 very simply, and this is all we got to know, the rate determining step, these things must be in the rate equation. They must be in the rate equation. They must be in the rate equation. All right. So the RDS, the slow things, are in the rate equation. So what's in the RDS? Well, according to the rate equation, oxygen molecules are in the RDS, aren't they? They're the rate determining step, and nitrogen monoxide. Two of them, in fact. So it must mean somehow the rate. Sorry, let me say this again because I don't think that's a good thing to say. It must mean the slow part of the reaction, must involve an oxygen molecule. We don't need the brackets anymore. It must involve an oxygen molecule and two nitrogen monoxide molecules, because that's what the order means. It means there's two of those and one of those in the rate determining step, in the slow step of the reaction. Let me skip on the slow start part of the reaction. All right, so that's what it means. All right, so is this a possible mechanism? Is this yes or no? Well, we've definitely got two of those, don't we? But there's no O2 in the slow part of the reaction. So this is not a possible mechanism. Why is it not a possible mechanism? Well, first of all, we've got to say no, it's not. And why is it not? Well, because according to the rate equation, an O2 molecule must be in the slow part of the reaction. All right. In other words, it must be in the rate determining step. Does that make sense? Any questions there? All right. Are we good? All right. The NO is there, but the O2 is not there. Lungi, you all right with that? Excellent. Have you learned anything today? Seriously, either of you? Are we good? Are we good? No. Oh, well, Helene says, I forgot the ideas. But you're good now. As long as we learn, you know what, Helene? As long as we learn something, I don't care what we learn. As long as we learn something, that's all I care about. All right, now I'm looking at the question. I think the question's over now, actually, that one. Right, now let's have a look at another one. I've got another one for you somewhere. Okay. Right, or do I? I thought I did. So that's the RDS for that. I'm looking at another one now. Thanks to Helene, by the way, for all her wonderful past papers, and that's a big deal. And as I've said a million times, guys, you've just got to hit the past papers one step at a time. That's all you've got to do. Right, there appears to be none on this one, all right, which is fantastic because I'm sure I had one lined up for you. Let's have a look. Nothing there yet. Maxwell distribution. Oh. All right, rates. All right, now I'm going to have to dig into. All right, let's go and find another one. That's weird that there's not. Oh, there is one there. Oh, that's not a very good one, but never mind. Let's do this one together. All right. I knew there was one on this page somewhere. I just didn't know where. All right, so nice and relaxed. Oh, nice and lovely day. What could be more? Springtime in Botswana. We're lucky. Lucky to be alive. Right, here we go. So I'm going to copy this one. This one doesn't look like a rate equation, but it is. All right, so let's get that to 100. Let's move this under there. Okay, and I'll whip through the top bits quickly. I hope I will anyway. Okay. Oh, God. And obviously, first of all, there's an equation. All right. Lignite type of coal contains about 0.4% of sulfur by mass. Calculate the amount of moles of sulfur dioxide produced when 500 grams of lignite undergoes combustion. Oh, you know what? I don't know about you, but I don't like these because they're trying to kill us, aren't they? Can you see the nasty bit? This is the nasty bit because it's not all sulfur. Only 0.4% of lignite is sulfur. So if we've got 500 grams of lignite, how much is sulfur? That's the thing, the annoying thing here. They're trying to mess us around. So this is what I would do. I'd start off with the mass of sulfur is, well, the mass of lignite is 500, but only, my internet's going, I think, but only 0.4% is sulfur. So times that by 0.4%, and this is going to give me the grams of sulfur. So here's my trusty calculator. 500 times 0.4 is 200. Is it as much as that? That's not 0.4%. What am I doing wrong? It's not 0.5. That's 40%, isn't it? All right, so I've got to divide that by 100, haven't I? So do you see what I've screwed up there? This is where I hope you realise I can screw up just as much as you guys, eh? Trust me. All right, so times 0.4 equals that divided by 100. But I managed to do it though, didn't I? Honestly, it's bad, and I'm not joking. I made a stupid mistake there, but what I'm trying to get across is that we all can make them. I'm supposed to be good at this, aren't I? All right, and we divide that all by 100 grams. So I screwed up, but there you go, 2 grams. So 2 grams of sulfur. So now, well, what's the number of moles of sulfur? It's 2. I'm going to cheat. I'm going to use 32 because I haven't got time to go to the proper periodic table. So 2 divided by 32 is going to give me this 0.0625 moles. Then I'm going to say, well, 0.0625 moles of sulfur is going to give me 0.062 moles of sulfur dioxide, isn't it? And I think that's the answer. I didn't realise. Answer is 0.0625 moles. Are we good? Everyone's good with that? That's an easy one, isn't it? That's an easy one. Now, I thought it was going to be harder, but 2 moles. Oh, well, that's a nice one for 2 moles. How can sulfur dioxide produce acid rain? Well, easy. Sulfur dioxide is a gas. It reacts with water in the atmosphere, which is a liquid, and it produces H2SO3. But that's not quite right. Oh, sulfur dioxide, that is right, isn't it? No, it's not right. Does anyone know why that's not right? Maybe you don't know it's not right. You don't know. What is acid rain? Do you know what acid rain is? No? Acid rain is actually not sulfurous acid. It's sulfuric acid. To be honest with you, this would get you the mark. This would get you the mark. Okay? Yeah. Well, it's not... I don't know, Emily. I'll try and explain in a minute. Let's start off first of all. That would get you the mark, even though I haven't got the answer scheme for this one. I should dig it out, shouldn't I? Hold on. Now I'm freaking out. All right. It's that one, and obviously, it's not giving me the year of the paper. These papers, these IB papers, they're such a pain. Right. That would give you the mark, but normally what happens is this. Sulfur dioxide undergoes atmospheric oxidation to form sulfur trioxide. So this is it. That happens first. And then secondly, then the sulfur trioxide reacts with water to form sulfuric acid. So this is a better answer. I've just rubbed it out, obviously. Right, there you go. This is a better answer. My bottom answer is better because there's 2 things going on there. But the top one it's only 1 mark. I think the top one will give you it as well. So acid rain the majority of acid rain is sulfuric acid. But this is certainly in acid rain. So that's not a wrong answer. Did you draw the dot and cross diagram for sulfur dioxide, the Lewis structure or whatever? Now, what does sulfur dioxide look like? It has an expanded octet, doesn't it? Do you know on Earth what I mean by that? Because don't forget, we're trying to learn some new chemistry if we can. Does that make sense? You know what an expanded octet is? No, okay, Lunga, that's fine. Well, let's dig around down here. Okay, so let's go down here. Sulfur. What's the configuration of sulfur? It's 1s2, 2s2, 2p6, 3s2, 3p, 4, I think. Yeah. Now, I'm interested only, believe it or not, I'm only interested in these outer shell ones. Okay. So let's have a look at 3s2, 3p4. And if we draw those in what we call electrons in boxes, all right, we get this. We get 3s2, 3p4. Okay, how many electrons are in there? Okay, let's use this. There's 2 electrons there. And this is 3, isn't it? 1, 2, 3, 4. So how many bonds in this form can sulfur form? Sulfur has two unpaired electrons, which is fine. There's nothing wrong with that. And if you mess around with sulfur, you can get something like this, hydrogen sulfide. And you can have no problem with the dot and cross there, okay? And as you can see, sulfur has 8 electrons around its outer shell. So it's got 1, 2, 3, 4, 5, 6, and then the 2 from hydrogen, 7, 8. So everything's good with sulfur. But you can do something weird, which is called expanding the octet of sulfur. And this is what happens here. All right. Oh, this is going to be scary for you if you've never seen this before. Okay. There's 3s2. What on earth am I drawing that for? This is 3s2. My internet is dying, I think, because it's not keeping up with me. This is 3p4, and these are 3d electrons. Okay, so let me cut them off with that. So there, and 2, 3, 4, 5. Now, normally, obviously, sulfur is 2 electrons there. 1, 2, 3, 4. And obviously, this at the moment is the same as this. But now I'm going to do something called expanding its octet. And one of these electrons there, the ones I've just rubbed out, gets promoted to the 3D. So how many bonds can sulfur make in this formation? Well, in this one, it has 2 unpaired electrons in the first one. But if you look here, it's actually got 4 unpaired electrons. Okay, and that means it can form 4 bonds. Okay, and now there's sulfur, and that is sulfur dioxide with its 4 bonds. 1, 2, 3, 4. They're the 4 bonds, plus the lone pair. And there you go. That's the Lewis structure of that. But let's draw it a bit more formally now. So we start off with sulfur. There's a double bond. 1, 2, 3, 4 with oxygen. And oxygen would be something like that. And then there's double bonds with another oxygen there. 1, 2, 3, 4. And then there's the pair there. So if you count the electrons around this sulfur, it's actually 10 electrons. Okay, and this phenomena is known as expansion of the octet because it's bigger than 8. Expansion of the octet. Okay, I can tell my internet's dying here because it's not keeping up with me. So do you understand that? Have you come across that concept before? It is, yeah. It's a bit of an annoying one. Helene, how about you? Yeah, do you understand it? If we expanded the octet further, we'd be able to get SO3 out of it. But I'm not going to do that now, I'm afraid. Okay, so there you go. That's expansion of the octet. That's how sulfur dioxide can exist. But try and figure that out, guys, because that's an important thing. All right, now I'm going to look very quickly because the video is going to run out any second. All right. So paste that there, make this 100, move that over there. Yep, my internet's dying. It's been awful. I had them in yesterday to look at it, And they said, no, there's nothing we can do. Oh, it sucks. Sodium thiosulfate reacts with HCl as shown. Precipitated sulfur makes the mixture cloudy, so a mark underneath becomes invisible. This is a classic experiment. It's lovely. Suggests two variables other than concentration that should be controlled when comparing the relative rates of the reaction. Now, one variable, obviously, which must keep the temperature constant. That's one variable, temperature. And another one, believe it or not, the flask used must be the same. Okay? Because the flask used is going to determine the depth of liquid there. And when you're looking down it, if you use a big, let me use a big beaker. Okay, imagine there, look at that. And it's the same volume. The volume is the same in both, but the depth is different. And so if you look down it, this one will take forever to the cross to disappear because you're looking through a very shallow depth of solution. But here you're looking through a bigger depth. So type of flask used, it must be the same. So should the volume of this stuff, whatever this stuff is, of the reacting mixture. That's got to be the same as well. All right. Discuss two different ways to reduce the environmental impact of energy reduction from coal. I'm not going to do that. You can look that up. These environmental stuff, this is on you. But guys, as you can see, they're on the exam. So learn this. Okay. All right. Discuss two different ways. So put this in your toolbox. As I used to tell my Ellisons, you go along the course and you learn things like this, okay? And you put them in the toolbox of your brain, okay? And once it's in there, it won't go out. Just put it in there to start with, though. All right. Now, guys, I've got to shoot now, I'm afraid. But it's been obviously a pleasure. I hope you found it kind of useful. Talking about this stuff. But please, you know what? These sessions are only as good as you can make them. So if you've got questions you want to ask, bring up specific questions. And now, how do you revise? Guys, one step and then another step. That's all you do. All right. Helene, it's a pleasure, dear. But please, if you get freaked out by anything, give me a call and we'll have a lesson, okay? Honestly, it's so important that you do well at this. All right. And we'll get through this together, I promise you. All right. All right, guys. What day is it today? It's Friday, so maybe Monday. We'll try for another one on Monday. Now, listen, you don't have to attend. It's beautiful if you do attend. I'd rather you do attend. Because if you attend, you can give me things you're having a problem with. But if you don't attend, I'll make a video and post it anyway. Okay. Anyway, guys, we'll take care. Have a great day and a great weekend. All right, take care and hopefully see you on Monday. All right, bye-bye.